Hello and welcome to this next lecture on fundamentals of acoustics. Last class we finished the solution to a forced finite fixed string. We will look at the details of that solution in this next class right now. So we found last time that the solution was of this form: f by tk sin k L minus x by cos k L e to the power j omega t. This is for the forced finite fixed string. Okay. This was the response we found last time. So now let us look at further details. Okay. So one thing we notice here is that when we did the infinite string, okay, the response was of the form I think f by rho L c e to the power of j omega t minus kx. Okay. Now if we take the real part, of that y tilde x comma t, what we get is f by rho L c cos of omega t minus kx. Okay. So in the argument we have both time and space combined. Okay. So this is a travelling wave solution. This is what is called a travelling wave solution. Okay. In contrast, what happened here? If I want now my real part of the solution, what I get is f over tk sin k L minus x over cos k L into cos omega t. Okay. So here we were unable to separate time and space, can't separate. Okay. So if I open out, it's cos omega t cos kx plus sin omega t sin, it's just a combined expression. Okay. Whereas here what do I see? This is a constant. This is a complete function of x, no time in it, it's a function of time alone, no space in it. So I have a separation. Okay. So I have a separable solution actually. Okay. So now why does this happen? So why does this happen? Okay. First of all, this is called a standing wave solution. Standing wave solution. Okay. Why a standing wave solution? Suppose sin k L minus x is 0 at some point. That means I am driving a string, this is my string, this is fixed, and the response is something, and there is in space a 0 and something happens. Spatially it is a 0. So this value is a 0, this value is 0, and so 0 times cosine omega t will always be 0. Okay. So this point will always be 0, it will never move, whereas the other part will be moving. Okay. Now suppose sin k L minus x is a maximum value, which is 1 or minus 1, whatever. Okay. So then that point will have a maximum value of 1 at some point in time, and it will wane slowly with time. As time progresses, as cos omega t changes, it is multiplied by this amplitude 1 coming from here, and as this value starts to reduce or go up, oscillate between +1 and -1, this value will change. Similarly, if there is some sin k L minus x value which is -1, like this -1, okay, that gets multiplied by cos omega t, and cos omega t changes from -1 to 1. So, it will have a waxing and waning effect. Okay. So, this is as though the wave is standing, the 0 point has remained 0, and around that, okay, the points have moved up and down, and so this is called a standing wave solution. As opposed to this, which is a travelling wave solution. In here there will be no points which are permanently 0. A wave will move, a wave will move to the right, a wave will move to the right. So, there is no permanent fixed points, every point goes through a set of displacements, okay, based on its phase delay. So, that is the difference. Now, there is a lot that we can see from here. So, one reason is that in the absence of dissipation, the disturbance due to the forcing moves at a certain amplitude, and it comes to the fixed point and gets reflected with the same amplitude. Okay. That is what we saw, the magnitude of B was equal to the magnitude of A. They may be phased differently, does not matter, okay, but the magnitude of B, the returning wave, is the same as the magnitude of wave of that is the forward travelling wave. That is the reason that you have an interference between equal amplitude waves that leads to a standing wave. That is one important thing. Okay. So, it is the B magnitude equal to A magnitude which has resulted in this form of separation. Okay. Now, let us look at the mechanical impedance. So, let us look at Z mechanical. Okay. Now, let me repeat my Y tilde x comma t is, I will take it in this form, f by tk sin k L minus x cos k L e to the power j omega t. Okay. Then my del y by del t is equal to j omega f by tk sin k L minus x by cos k L e to the power of j omega t. This is my velocity, and I will get the velocity at x equal to 0. So, x goes to 0. So, I get j omega f. Let me simplify this. T is rho L c square, k is omega by c, I am setting x to 0, so I get sin kl by cos kl, and let me keep e to the power j omega t. So, this happens to be my v tilde, okay, and this is e j omega t. Now, my z mechanical is equal to f by v tilde, right. My f is what? F tilde is f e to the power j omega t. So, f is the amplitude. So, z mechanical tilde is f by v tilde. So, v tilde, if we simplify a little, this omega goes, this c goes. So, I get j f by rho L c tan k L e to the power of j omega t, okay, and this is v tilde. So, if I compute my z mechanical, f by j f by rho L c into tan k L, that ends up as my f cancels, I get minus j on the numerator, tan k L becomes cot k L, and rho L c goes up, rho L c. So, that is my z mechanical, okay. So, my z mechanical tilde is minus j rho L c cot k L. So, observation right away is purely imaginary. Okay. So, let us see what this means. The z mechanical is minus j rho L c cot k L. Now, what is happening? My z mechanical was supposed to be, could be complex with a real part and an imaginary part, okay. So, what this is saying is that my real part is 0, and real part, what have we learnt? One is it indicates dissipation, okay, in the material. Two is it indicates power dissipation by the force, power injected, okay, as an average over a cycle, over a time cycle, time t, okay. So, now what is happening is that we have a finite string that is fixed over here, okay, and we are forcing it over here. So, this forcing agent is saying there is no dissipation, of course, because in the material there is nothing to dissipate. However, over a time cycle t, time period t, I am not injecting power, no power, no average power. And that is because the incident amplitude A tilde gets reflected from this zero displacement point. It has the same amplitude B tilde. So, he says whatever I am sending in, A tilde is coming back to me, okay, as B tilde, and therefore, no average power. Okay, and therefore, the real part is first of all 0, and therefore, the non-dissipative elements okay, of a vibrating system. What are they? Damper. I mean, typically what do we say? We start a damper, we talk of a stiffness spring type, we talk of inertia which is a mass. These are the typical elements of a dynamical system. So, the non-dissipative elements, that means no damper, the stiffness and inertia will be present. Okay. So, the forcing agent is saying that there is no R is equal to D0. Why? Because A tilde magnitude is equal to B tilde magnitude, no average power, and therefore R is 0. However, the other elements are there, stiffness and inertia, and therefore the X part will be there, and so that is J times minus rho LC cot KL. So, all these are tied together. The A magnitude equal to B magnitude is tied to the R being equal to 0, is tied to there being no dissipative elements, is there tied to there being only stiffness and inertia, okay, which means a purely imaginary impedance, and therefore a standing wave. Okay. And further we will see that what did we say? We said the X when it is set to 0, X when it is set to 0 gives me an equation for computing resonances. Okay. So, if I now set minus rho LC cot KL to 0, rho LC are not 0, which implies cot KL equal to 0, which implies cos KL equal to 0, then I will find an equation for resonances or the natural frequencies. Okay. So, what are those? So, let us see, we have cos KL equal to 0, okay, and so there are many conditions, many values of KL for which this happens. So, this is going to be KL is going to be twice n plus 1 pi by 2, okay, n going from 0, 1, etc. Okay. So, my Kn, K acquires an index now, n index, which is twice n plus 1 pi by 2L, okay, and Kn is what? Omega n by C, omega n is what? Twice pi Fn by C. So, my twice pi Fn by C is equal to 2n plus 1 pi by 2L, okay. So, that my Fn in hertz, the resonance frequency in hertz is given by twice n plus 1 C by 4 L. Okay. Now, you remember the response y tilde x comma t is, let us see, f by tk, f by tk sin kl minus x by cos kl e to the power j omega t, and so when cos kl goes to 0, y tilde blows up, goes to infinity. Okay, this is the resonance frequency. Actually will not blow up, but we have not put any damping, so that is the ideal result. Okay. Now let us look further. So now we have found that the system has resonances. That is also a consequence of there being a finite string, okay, with A amplitude being equal to B amplitude, that results in R equal to 0, which results in purely stiffness and inertial elements being present, which results in a standing wave, okay, and therefore you can have resonances. So finite systems have resonances. Finite systems have resonances. Because there is going to be an incident wave, and because of the finiteness there is a boundary, and there is going to be a reflection from the boundary. Okay. For now let us understand it in this way, that the incident and reflected, they have equal amplitudes, okay, and there is no dissipation in the system. That is why we have resonances, and all the consequences, okay, A magnitude equal to B magnitude, R is equal to 0, okay, and standing wave solution, and resonances. Resonances I have already put, standing wave solution, yeah, and x not equal to 0. Okay, these are all tied together. Okay, even when you have a small amount of dissipation, there can be resonances, etc. Let us not discuss that part over here. Right now our systems are non-dissipative. Okay, so R is equal to 0. Okay, that results in A tilde being equal to B tilde, that results in a standing wave solution, okay, and x will not be 0. So let us understand it, that these are all tied together. Now if you want a further insight into the condition of resonance, okay, pictorial, let us say pictorial understanding of resonances. Okay. So cos KL is, so what, let us say that we KL, right, KL is what, KL is omega by C into L. Okay. So now omega, we start at a very low value, okay, that means k is a very low value, that means twice pi by lambda is a low value, so that lambda is a very large value. Okay. So omega low, k is low, lambda is high. Okay. And I have my string over here, string of a certain length, fixed at this end, forced at this end. Okay. So I start off low k and high lambda, so the lambda will be large, so let us reposition. So this is my finite string, let us say, okay, and lambda is large. So lambda is large means what? It goes off. Okay, 1 lambda is what? positive and negative 1 lambda, right, this is 1 lambda. So, lambda is very large means the 0 and etc. will come much later, it is much larger than k, I mean L, much larger than L, that is what we mean by high. Okay. Lambda is much larger than the length. Now we come, as we go raise the value of omega, okay, we come to a position where first time so cos scale will be 0, right, I mean sorry, cos scale will be 1, approximately 1, right, when KL is very low, cos scale is approximately 1. Now somewhere as omega is increased, KL is increased, cos KL for the first time becomes 0, first time it becomes 0. So what is that value? KL is pi by 2, okay. So that twice pi by lambda into L is equal to pi by 2, pi goes away, L is equal to lambda by 4, or lambda is equal to 4 times L. Okay. So lambda was very large and it has become, lambda is becoming smaller as k is becoming larger with omega, and suddenly we have a situation here, a lambda happens to be 4 times L. So if I draw one lambda, let us see, I draw one lambda, this is half a cycle, so I will draw it the other way, this is half a cycle and this is the other half of the cycle. This is full lambda, one full wavelength, okay, and it is 4 times the length of the string. So the string is fixed over here, so this is where my string ends, okay, this is my string ends. So I am forcing it over here, it is fixed. So this is 1 L, this is 1 L, this is 1 L, this is 1 L, that is how lambda is equal to 4 times L. So we are not interested in this part, we are not interested in this part, right, because the string is only this much. So if I make it bigger, if I take the relevant part of the string and plot it or draw, this is my string fixed here and forced here, and the wavelength is moving like this and it reaches a peak, it reaches its first peak over here. Okay, it reaches its first peak over here. That means what? The frequency is such, the frequency is such that the maximum amplitude occurs at the driving point. We are looking at single frequency excitations. Okay. The single frequency will result in a single wave number k. Okay. So it will be aligned with the boundary conditions. So here is the 0 condition. So if I plot my full wave, it is going to look like this. Okay. And if I plot it along with the string, it looks like this. So the maximum value of the displacement is aligned with the driving point at this frequency. That means what? The forcing finds 0 impedance right, cos KL is 0, cos KL is 0. That means my minus j rho L C cot KL is 0. So, impedance is 0, that means easy to drive, right. Infinite impedance hard to drive, 0 impedance easy to drive. Why easy to drive? Because the maximum of the wavelength aligns with the forcing location. Okay. The string is saying it is very easy to drive me. Why? The wavelength is aligned in that manner. Okay. So, now if we look at the next, 0. Okay. So, we have got an understanding why the resonance happens, right. It is easy to drive the string. Now, let us look at the next value where cos KL goes to 0, cos KL goes, the next value is KL is 3 pi by 2, it is not B pi by 2, 3 pi by 2, 3 pi by 2. Okay. So, now what? Twice pi by lambda into L is equal to 3 pi by 2, pi goes away, okay. L is equal to 3 lambda by 4, that means length is 3/4 of lambda, okay. The string length. So, now the frequency has gone up further, omega has gone up further, so that k has gone up further, so that lambda has come down further. Okay. Now, what? The length of the string accounts for 3/4 of lambda. This is my length now. Okay. If lambda is this much, the string occupies this much, the string occupies this much. Okay. So, if I try that, let me, this is half wavelength, let me draw it the other way, this is half wavelength and this is a quarter wavelength. A quarter wavelength. Okay. So, this is 3/4 lambda, full lambda would be this much. So, this is how much the string is, how long the string is relative to lambda, okay. And this end is fixed. Now, again the forcing location is seeing a maximum of the wave, okay. And so, cos KL is 0, which means the Z mechanical impedance is 0, easy to drive the string. Why? Because the maximum is aligned with the forcing location, okay. And so on. And the next will be even more complicated, okay. You will have a full wavelength and then quarter, etc., etc. So, that is how the resonances happen physically, okay. The maximum point of the wave aligns with the forcing location, okay. Now, let us just briefly look at an anti-resonance. So, if we look at an anti-resonance, that means what? Cos KL is equal to 1, okay. which means we will take the +1 points for now. Okay. So, KL is equal to twice n pi. Okay. So, what does that mean? The first time it happens is twice pi. Okay. So, twice pi by lambda into L is equal to twice pi okay. So, then my L is equal to lambda. Okay. So, now I have a string, this is my lambda, this is my lambda, that is also, this is my lambda, okay, and that is also equal to the length of my string. So, the 0 point of the wave, the node point of the wave or the 0 point of the wave has aligned itself with the forcing location. Okay. And so, what happens now? The impedance is no more 0, cot KL, which is cos KL by sin KL, where cos KL acquires a value of 1, sin KL acquires a value of 0. Therefore, this is infinity, impedance is infinity. Why impedance is infinity? Because the wave is aligned such that the 0 point of the single wave number comes and aligns its 0 with the forcing location. So, the forcing agent says that I can't move it, I am sitting at a node point. The string, it does not even see me. Okay. At this frequency the string is not even seeing me as an agent, okay, and so I can't drive it. Okay. So, you have an anti-resonance. Okay. In fact, if you look at the expression y tilde x comma t, it is some constant in front into sin k L minus x. So, if x is 0, I am looking at the starting point, it is sin k L by cos k L e to the power j omega t, and you can see cos k L is 1, sin k L is 0. So, the displacement there is 0. Okay. So, the force is sitting on a 0 displacement point. So, if I have a bridge, and it is supported by these columns, so there is a river flowing or something, and this bridge is across that river and supported by these huge columns, okay, and this is a 0 displacement point because it is very rigid. If I try to drive it over here, I will not be able to drive it, whereas in between these two load point, support points, if I drive it, and I can get a response over here, right. So, this forcing agent is sitting on such a location that it is not able to drive it. Okay. Then how do we understand this? Okay. How do we understand this? That you can't drive it, okay, and you are having a response also at other points of the string. There seems to be a contradiction, right. I am sitting at a 0 point of a string such that the string will not accept any forcing, but the string has a displacement. How the energy must have gone in, right, for the string to actually, well, we are looking at an idealized situation, okay. In actuality there will be some dissipation, some dissipation, okay. And right away the string is not going to acquire this shape, there will be some transients, okay, and because of the dissipation there will not be a true node point. All these aspects will come so that the driver can pump some energy, okay, can inject some power, okay. All these things will result in a response, but we are looking at an idealized situation of no dissipation, no transients, etc., etc., okay. So in our situation we will have a node point and the string will also be driven, have a response at other points, okay. So now I will close the lecture here, okay, and the next class what I will do is we have been looking at this complex notation, and I know many students in the beginning are not comfortable. So I will show you that if you take the real values right from the start, how cumbersome it can get, okay, so that immediately you will start liking the complex notation. So we will do that in the next class. Thank you.